I wanted to kind of talk more about how we can do everything we can to squeeze your advanced neural network designs into embedded systems, right? That's really what this talk's about. And I think there's been a lot of researches and a lot of advancements in different techniques like pruning, quantizations, lower precisions. Now, this talk will focus on the pruning as one of the key techniques. Oh, here. So this is going to be a big repeat. I'm sure everybody's been hearing this all day long. But we've been seeing a huge revolution, right? Going from embedded vision system, like traditional vision systems where we talk about cars with, say, mono cameras, stereo cameras, becoming autonomous systems, where you have many, many sensors and lots of teraops of neural networks together to do very intelligent processing. And this is not only for cars. Surveillance, machine vision, drones, medical, all those opportunities, right, becoming much more intelligent. And we like to call it autonomous systems, because cars clearly are becoming autonomous cars. But if you think about it, drones are the same, right? They're autonomous flying robots, and so is the factory robots. So they're all heading in the right direction. So when you look at all these different applications, which we bundle as embedded vision, we clearly see a huge mandates and requirements coming from markets and the customers, right? One, all these systems has to be more intelligent. That means you have to have order of magnitude more processing using neural networks, plus traditional computer vision, plus sensor fusion. Now, it cannot come with a cost of longer latency or more power, right? So you still have to react within, say, 100 milliseconds of your sensor detecting something abnormal, and your efficiency, right? Lots of those cameras are still mounted under the windshield or in the power over Ethernet type of environment. So you really have to have a top ceiling of how much power you can consume. So all these design constraints are still there while you're trying to squeeze order of magnitude more computation in there. So this is 3 mission impossibles, if you call it, right? But we have to make that happen. That's why there's no perfect chip out there. And in a way, everybody's competing for the perfect chip. But meanwhile, I think the flexibility to upgrade is a key, right? Every week, I'm sure you see new inventions in the neural networks. Tomorrow, people are going to come up with some crazy ideas that completely change the topology or bit width or pruning techniques. And this is true for algorithms like neural networks, but also sensors, right? I don't think everybody agree that these are the set of sensors that you use for autonomous cars or drones or robots. I think the innovations continue to happen. That means your hardware platform has to be flexible for different type of IOs and standards. And as you know, we're all connected today, right? Clouds, edge to cloud. So you have to support all sorts of different standards, and this is the bread and butter for FPGAs.